Building a machine learning model is a lot like following a complex recipe. Pre-processing requires the meticulous preparation of your ingredients before you turn on the stove. A dataset with 0 obvious missing values might look perfect on the surface, but if your categories are left as text and your numerical features span wildly different ranges, it is completely unusable for an algorithm. Throwing more data at the problem does not eliminate this step. If you scale up a dataset with poor encoding or unscaled features, you are just training a poor model faster. Our goal is to build a systematic, step-by-step structural pipeline. We need to take messy, raw data and transform it into mathematically viable inputs. The quality of your data strictly dictates the quality of your model. Every step in the pre-processing pipeline represents the core work of the machine learning process. The first step in our workflow is identifying and treating missing values and duplicate rows. If you use automated imputation to fill missing gaps with a generic mean value, you risk artificially distorting the data's natural distribution. You are making a guess, and the model will treat that guess as fact. Alternatively, you might choose to drop incomplete rows. But if you drop rows from users who systematically decline to provide their income, you introduce selection bias by completely silencing a specific demographic. There is no single correct strategy here. Dropping data loses information, while filling data invents it. Every choice carries a trade-off, and choosing poorly silently damages the model's worldview. Before we make any transformations to the values themselves, we have to perform the absolute first mathematical step: the train-test split. This separation is essential for evaluating the model fairly. We divide data 80-20. The model learns from the 80% training set, while the test set is held back. If test data influences scaling parameters, it causes data leakage. Fitting a scalar before splitting leaks test statistics into training, providing an unfair advantage. To ensure your split is reproducible across different runs, you use the random state parameter in your code. This locks the specific data division in place. Models evaluated on leaked data will produce misleadingly optimistic metrics. When that model is deployed to production, it is guaranteed to fail. Next, we address text. Algorithms cannot read words. They require numerical vectors. We bridge this gap through categorical encoding. We use label encoding to preserve order for values like low, medium, and high. But for parallel categories like red, blue, and green, we use one-hot encoding to prevent the algorithm from assuming red is mathematically smaller than green. One-hot encoding carries a mechanical risk. It dramatically grows your dataset. It transforms a single column into many separate binary columns, which can severely slow down training on large datasets. Algorithms take numbers literally. Choosing the wrong encoding method forces the algorithm to learn false mathematical relationships that will heavily skew its predictions. With our text converted to numbers, we turn to feature scaling. This is the process of adjusting disparate numeric features so they share a comparable magnitude. Extreme salary ranges from 20,000 to 120,000 overpower smaller numbers in distance calculations. Standardization solves this by mathematically shifting data so the mean is exactly 0. Alternatively, normalization strictly compresses all data between absolute 0 and 1. Most general-purpose algorithms depend on comparable magnitudes to calculate distances efficiently. Feeding them unscaled data cripples that internal math. In professional environments, these transformations are never done ad hoc. They are formalized into an immutable sequence called a pipeline. When a model is deployed, any new data from the real world must pass through this exact same sequence in the exact same order. If it doesn't, the model will fail to interpret the inputs. These clean, scaled inputs are exactly what we will feed into our first regression models in Topic 2.1, and that held-out test set is what we will use to accurately evaluate them in Topic 2.6. An intelligent model is useless without a bulletproof pre-processing pipeline to feed it reliably. Build the structure first, and accurate predictions